Every millisecond, networks process millions of events. A credit card swipe in London, a server ping in Tokyo, an IoT sensor on a factory floor. Finding the single fraudulent transaction or failing component in that massive, chaotic stream is the core challenge of modern anomaly detection. For decades, the standard response was to strictly define what constitutes normal. Algorithms were built to mathematically map out every single variation of safe, expected behavior. Methods like one-class SVM or distance-based models do this by plotting data geometrically. They locate the densest clusters of everyday activity and then calculate complex, undulating boundaries to wrap around those safe zones. Anything falling outside that line is flagged as an anomaly. But mapping every safe transaction takes massive computing power. The system expends the majority of its energy obsessing over mundane everyday data, just to figure out what doesn't belong. When you apply these distance-based models to modern datasets holding dozens or hundreds of features, the underlying math breaks down. To check if a single data point is an outlier, the algorithm has to calculate its exact distance to every other point in the network. While this is easy for a few points, it creates an O(n)² bottleneck at scale. The server crawls to a halt under the weight of calculating every possible connection. To handle data at this scale, we have to stop trying to map the normal entirely. We have to do the exact opposite. In 2008, researchers proposed a shift in strategy based on a simple observation. Anomalies are few, and they are different. Because they are rare and sit far away from the average, they are highly susceptible to being isolated. This concept drives the isolation tree. Instead of carefully measuring distances, the algorithm takes a dataset, randomly selects a feature, and slices the data with a random split value. Then it recursively does it again. This plot shows a dense central cluster undergoing random slicing to isolate the point labeled xi. Because xi is tightly surrounded by similar data, separating it requires dozens of random splits. Its path length down the algorithmic tree is exceptionally long. Now look at the anomaly xo in the sparse margins. Far from the norm, just 3 partition lines isolated completely. This reveals a direct mathematical rule. A shorter path of random splits directly correlates to a higher anomaly score. By using random partitioning, the anomalies are forced to expose themselves. The algorithm bypasses complex density or distance calculations entirely. A single tree relies on pure randomness, which makes it statistically unreliable. The algorithm fixes this by building a forest of 100 to 200 randomized trees. This graph tracks how the model stabilizes. As more trees are added, the average path length for the normal point, xi, flattens at a high value. Meanwhile, the anomaly, x0, stabilizes at the bottom with a consistently short path. Average path lengths are translated into a normalized anomaly score. A shorter expected path length drives the score up toward 1.0, flagging it as an anomaly. Scores hovering near 0.5 require average effort to isolate, marking them as standard noise. When you apply this scoring across a full dataset, you get this contour map. The forest identifies the high-score anomaly regions, shown in the lighter 0.7+ bands, wrapping around the outer edges, all without ever calculating point-to-point distances. By focusing on isolation rather than profiling, the forest achieves linear time complexity. This bypasses the processing bottlenecks that typically prevent anomaly detection from scaling to massive datasets. But the algorithm does have mechanical blind spots. It struggles when the sample size is too large, falling victim to 2 statistical phenomenons, swamping and masking. Swamping happens when normal data crowds the space so heavily, it forces the trees to make extra splits to isolate an outlier. Masking occurs when anomalies cluster so tightly together, they trick the tree into treating them like normal data. The fix is paradoxical. Where traditional machine learning models crave more data, the isolation forest becomes more accurate by randomly dropping 90% of it. By limiting each tree to a small subsample, often just 256 instances, the algorithm clears out the noise. The masking effect breaks, and the random splits can cleanly isolate the true anomalies once again. Building partial models from these tiny subsamples is exactly what allows the algorithm to maintain its accuracy, even as the total volume of data grows. The efficiency of the forest is undisputed, but the transition to production reveals a critical vulnerability. Industry benchmarks show that 64% of these deployments fail to deliver accurate results. The culprit is the contamination parameter. This is a manual setting where the user must guess the expected percentage of actual anomalies present in their specific dataset. If you guess even a few percentage points too high, you flood the system with false positives. Guess too low, and you let real, damaging fraud slip right through the forest undetected. No algorithm can determine this threshold on its own. It requires a human domain expert to look at the scores and define what level of statistical weirdness actually warrants a real-world response. The isolation forest demonstrated that random partitioning can speed up detection while exposing the rarest data points. However, the final classification depends on the human judgment used to interpret those results.